والسلام عليكم مع فيديو جديد. أنا توني وهذا chapter 5 خاصه بس بجريد 12 term 2 called current and resistance part 1. Why part 1? لأن there will be part 2 regarding how to solve questions connected to this chapter. So how to solve these questions? You can go to Classkick and this is the code and you are free to solve those questions. Okay, so I will do a specific video regarding those problems. All right, so welcome back لإلكم ولإلي كمان. Okay, يلا here we go. إن شاء الله ما يكون فيديو طويل. Okay, so these are our objectives for this chapter. Of course, as you see, some of them are required, others are for just arrangement. Okay. So the lesson started with the definition of electric current and with a picture of 6 small circuits, as you see, A, B, C, D, E, and F. So in part A, the switch is open, so of course the light bulb will be off. In part B, everything's okay, the light bulb is on, shining, the same as C, but what's the difference between B and C? It's the polarity of the battery. So this is not important in that case. In both cases, the light is on. What about part D? As you can see, the light start to dim. It's the light bulb is on, but not like B or C. It's shining just a little bit. What about E? In E, we have 2 batteries and 1 light bulb. So here it's what called as super shining. It's too brilliant. In this case, the light bulb is too brilliant, as all of us, of course. And in part F, the light bulbs are parallel. So there will be, of course, a specific section talking about just that case in our chapter, where the devices or the light bulbs are in parallel circuit. Bon. Okay, here also talking about the current and charges. It's so difficult to, or it's we cannot separate the current I, which had the unit of ampere. We cannot separate it. It's separated from the charges Q. Remember in term 1 we studied the charges, Coulomb's law and Coulomb's equation. So that talking about the charges. So this chapter is a continuation of term 1. So in this case we are elaborating on the current. I is equal the derivative of the charge over the derivative of the time. Okay, so I equal dq over dt, or you can write it in another way where q is equal to the integral of I dt. What about the unit? So of course I is defined as ampere, the coulombs in the charge in coulomb, capital C, over the time, which is in seconds. Well, here we are in our chapter. Also we continue with the spectrum, electric spectrum. So why it's so important to study electricity? Because it's everywhere. As we see here, this is the electric spectrum that's going from the scale of 10 to the power of minus 12. Can you imagine? This is what we call by tunneling microscope. And that's, by the way, how we notice the existing of atoms. We cannot see atoms from our eyes, right? Because they are super or extremely small. So we can see it from such things called tunneling microscope to something that's extremely or astronomically big, to the power of 10, to the scale of 10 to the power of 10. Okay, here talking about the heliospheric current sheet. Okay, it's interesting to do a research about this, also about the aurora. It's so beautiful to know about such things. So you see, electricity is everywhere in our daily life. Here we are, a new term for us. I'm sure that it's your first time you meet such a term, current density. Usually we compare the current density to the flow of water. So here we have two pictures of the flow of water. question: in which picture the flow of water is more aggressive, more important, more significant? Okay, so of course, in this picture here. So both of them have a flow of water, but in one picture, the flow of water is more aggressive, making more damage, as you see here. So that's what we call in physics by the current density, and we refer it as J. So that's the symbol of the current density. Why you are studying the current density? Okay, so because we are interested in the flow of the current in the wire. Okay, and that's what we mean by the current density. So imagine we have a wire, the charge are flowing into the wire, as in the water, the water in the pipe are flowing in the pipe. Here the same, the charge are flowing in the wire, and that's what we mean by the current density. So there is an equation for such thing where J, okay, which is the current density, is equal to the current I. It's equal to the current I over the capital A. What do you mean by A here? It's the area. It's not the ampere. Please don't be confused between these two A's. Okay, so in this equation we have two A's. One A is the unit of the ampere. Sorry, it's the unit of the current, which is the ampere. And over, or it's in the denominator here, the capital A, which is referred to as the area. As you see here, we have the wire, the opening of the wire. It's like a circle. Okay, so we have to calculate the area of that opening. Okay, or you can write it the equation in another way, where the I, the current, is equal to the integral of J, which is the current density, multiplied by dA. Okay, if you go to Classkick, there is a small question regarding this equation. We continue to section 3, where we're talking about resistivity and resistance. By the way, I need a volunteer, please, someone from the viewers, to please write the number of the slide, which is related to the number of, or the page in the book, please. I forgot to put that on on my PowerPoint. Please, I need someone to put, for example, here the section 5.3, it's which page in our book, please. I need someone to do that. So when talking about resistance, of course, we have, or we must talk about Ohm's law. Of course, most of us, or all of us, are familiar with Ohm's law, where we can write that the current is equal to the voltage V over the resistance. Okay, we studied this last year and the year before, and that's the triangle of the equation. Okay, we can write this equation in different ways. You can modify and arrange the equation, depends on the given. So it's interesting to talk about resistance because resistance always stop the flow of water, stop the flow of current, stop the flow of the motion. That's what we mean by resistance, something that stop the flow. Okay, so here please be interested. Look at the image here at the center. We have two pictures. Here the flow is straightforward. What do we mean by less resistance? There is no resistance in this case. What if we decrease the area, or we shrink the pipe or the wire? Now imagine you are the water, or imagine the flow. Here in this case, the flow will be difficult. Sorry, the water will be difficult to flow, right? It's more difficult. Why? Because the area now is smaller. So the water will not be comfortable moving through this opening, right? Okay, so what can we conclude from that? We conclude that resistance is proportional or inversely proportional to the area. Okay, let's go back to the equation of the Ohm's law. In Ohm's law, where the voltage equal the resistance multiplied by the current, it didn't mention the area. Okay, so we need to find a new equation that contains the component of the area. You understand what I mean? In Ohm's law, he didn't mention the idea of the area, but as our experiment here said, that area exists and affects the resistance. So every time the area is small, the resistance is big. Okay, another idea. Imagine the liquid, the nature of the liquid. The flow of water is different than the flow of oil. It's different than the flow of honey, right? The flow of oil, it's super easy, right? It's so easy for the oil to flow. However, if you can imagine the honey, it's so difficult for the honey to flow. Is that right? So the nature of the liquid also affect the resistance. It's not only the area, it's the type or the nature of the liquid. The nature of the liquid we refer to as the resistivity. So this is the new equation. Okay, so we have Ohm's equation, which is voltage equal to the resistance multiplied by the current. That's the old one. And this is the new one, where the resistance is equal to the rho, we refer to as the resistivity, which in other words, it's the nature of the liquid, or here in this case, the nature of the current. Okay, and over the area, that's the area inversely proportional to the resistance. What about L? L is the length of the wire. Okay, so here if you go to Classkick, I will remind you of that code also. You can solve this question. I will do a specific video on that solving such questions. Okay, opposite عكس resistance. Opposite to the resistance is the idea of conductance. Okay, so resistance, something that stop the flow of current, stop the flow of water. The conductance is the opposite. It push, okay, it encourage the flow, not stop the flow as the resistance. However, it encourage the flow. Okay, so that's what we refer to as in physics as conductance. Okay, okay. So the unit of the conductance is J, as you see here. You can zoom in, which is equal to the inverse of the resistance. As you see, it's 1 over R. It's opposite, or sorry, not opposite, it's the inverse of the resistance. Okay, so if resistance is equal voltage over I, the conductance G is equal to the I over the voltage. Okay, so the unit of the conductance is S, unit of current is ampere, and unit of voltage is volt, of course. Okay, here we continue. So where we have less resistance, of course, there will be more conductance. More resistance means less conductance. Why? Because they are opposite to each other. Good news, we are halfway to the end. And this is another example or another problem to solve that I invite you to solve on a Classkick. Okay, and this is a small hint for you to solve this question. I give you the two equations. You can play, you can modify those two equations to get the answer. Okay, still in section 3, we're talking about the rho. I'm sure that it's a new concept for us. The rho or the resistivity, which is equal to E. Do you remember what E in term 1? E referred to as the electric field over J, which we just defined as the current density. Okay, so this is the unit study where the rho is equal E, the electric field, over J. So electric field, of course, as you remember, it's the voltage over the yes, voltage over meter over the current density, which is area over meter square. Sorry, ampere over meter square. You see, I am also confused. So J is also equal to the ampere over meter square. So at the end, you simplify the units. You got at the end that conductance is equal to the omega, which is the resistance multiplied multiplied by meter. Bon, we continue. So what if something is missing here? So rho we refer to as the resistivity. But what about the conductivity? We refer to the conductivity as the sigma. Okay, so the sigma is the symbol of the conductivity, as rho is the symbol of the resistivity. Okay, so conductivity is the sigma, and it's equal to 1 over rho. Okay, another example here, it's a concept check 5.1. If at the that also you can find it on Classkick slide 3. The question is, if the diameter of wire is doubled, so diameter is multiplied by 2, what will happen to the resistance? What do you think? So I need your answers on Classkick, please. We continue section 4. Please, if someone can also please put the number of page for this section, I will appreciate that. So here, electromotive force and Ohm's law. So this slide, all in all, is about the unit of the charge. So if you remember, in term 1, we write the unit of charge as Coulomb, right? Capital C. But in this chapter, we can write it in another way. One, let's say, you can find this in your book also, that 1 milliampere per hour. So ampere and hour, does this remind you of something? Ampere and hour? It's the current and time. So of course we are talking about the charge. If you go back to the beginning of the PowerPoint, if you connect the ampere or the current with the time, hour, you got the charge. So 1 milliampere per hour is equal to 3.6 Coulomb. Okay, here is another example, slide 4. Another example or problem number 60, and this is a small hint. I write for you the given, the charge in milliampere per hour, or you can write it, you can convert it to Coulomb. We have the voltage 1.5 volt. We have the power 5 watt. So asking for the time because they said how long will it be able. So how long means or referred to as the time. We continue. Here is a 3D picture of a circuit. So of course a circuit contains a battery and a resistance. Okay, all circuits contain these two fundamental elements, a battery, VEMF, or the resistance R. So I need you to imagine that the battery is like the pump of the charge, something that's pushing the charge. So that's the function of a battery. It's also resemble or it's similar to the function of the heart. The heart also is pumping the blood in our body. The battery is also the pumping the charge into the circuit. So it's raised the pump. So look at this 3D picture. So this is the battery here. If you can see, this is the battery. It's raising the voltage. Okay, so it's pumping, it's giving a push, right? So the current flowing through the wire and then meet the resistance. The function of a resistance is opposite to the function of the battery. Look what's going on here. There is a drop. Can you see? So here there is a drop in the voltage. So here we have what we call by voltage gain across the battery. Across the resistance, we have a voltage drop or potential drop. So we can write that the battery will be referred to as potential gain. However, the resistance is called potential drop. Okay, so this is a 3D picture of our circuit. We continue with the section 5, resistors in series. I'm sure that you are familiar with such concept. So this is a picture of a series circuit where the resistance are connected through one wire, okay, all the way, straightforward. So how to calculate the resistance in this case? We just add their values, individual values. So R1 plus R2 plus R3. So this will be the equal, so that will be equal to the total resistance of the circuit. What about the current? The current is the same everywhere in the circuit because it's series, so the current is all or everywhere the same. Okay, what about the voltage? If you put two batteries or three batteries, we have to add their values. So if we have two batteries, so the voltage across the circuit will be equal to V1 plus V2. Okay. Okay, here is a small question. What are the relative magnitudes of the two resistors in this picture? So I know it's already 20 minutes بس بقي لنا شوي بقي تقريبا less than 10 slides and we finish. Please need your patience. So here we have a small picture of a circuit and 3D also, okay, a representation. So what do you think that which resistance, R1 or R2, which one is bigger or stronger? or more significant? Which one do you think? When looking at this picture here, the 3D representation, you can see that R1 drop just a little bit the voltage. But what about R2? Look at the drop, how big it is. Okay, so we can deduce that A is the correct answer, where R2 is bigger than R1. Okay, because the drop, look at the value here. Okay, you can see the value of drop on R2 is more significant or more important than the one represented by R1. Okay, here is also a small question, or let's read this before solving the question. So no matter how many resistance or resistors are in the circuit, just remember we are only talking about series circuit. Okay, the current flows into the first one is the same as the current that flow. So as we remember the table in the past slide, that the current is the same everywhere in the circuit. So the current passing through R1 is the same as the current passing through R2 is the same as the current passing through R3. So we hear it. Let's go to the question 5.4 concept check. Three identical resistors R1, R2, and R3 are wired together. So an electric current is flowing through the three resistors. So the current going through R2 is the same, of course, as the current going through R1 and R3. Okay, because there is no other way. Okay, it's a series circuit. The current will pass, the same current will pass through all of these devices. Still in section 5, talking about the parallel circuit, and here is a small comparison. First comparison between the shape of the circuit, look how parallel they are. Okay, here the current can have the option to be divided into two wires, okay, or two paths. Okay, let's look here. There is another way to calculate the resistance in the parallel circuit. I'm sure that you are familiar with that. Okay, so 1 over R is total is equal 1 over R1 plus 1 over R2 plus 1 over R3 and see the suite. So that's how we calculate the total resistance in case of parallel circuit. Okay, how to calculate the current in parallel circuit? We just add the values I1 plus I2 plus I3, okay, etc. However, in a series circuit, the current, if you remember, is the same everywhere in the circuit. Here in parallel circuit, we have to add the values of the current. What about the voltage? If you remember, in series, we add the values of the voltage. But in parallel circuit, the voltage across the sections is the same everywhere. So voltage across R1 is equal to the voltage across R2 is equal to the voltage across R3. So this is a small introduction for 5.5. And here is a small question. Okay, you can solve it also on Classkick. You can find, you can write your answers on Classkick. Here is another question as well. You can find it on slide 4. Yes, on slide 4. And this is the small hint that I provide you with a small picture. Okay, so here a potential difference of 12 volt is applied across a wire. The cross-sectional area, here is the area, which is 4.5 millimeters square. The length is 1000 kilometer. It's too long. Okay, so the current passing through the wire is that much. That's the value of the current. So asking for the resistance. Okay, what's the type of the wire? I change it to the resistivity. So please calculate the resistivity instead of find out the type of the wire. Please find the resistivity. Okay, we continue with another question. Okay, here we have three different circuits. They are asking asking us, yes, where to find the highest resistance. Where the resistance is the highest. Is it in circuit A, circuit B, or circuit C, or all are the same? Okay, so I need you to think about that and put your answers in slide 5 on Classkick. We continue on with a small example. Equivalent resistance in circuit with 6 resistors. So here we called as complex circuit. because it contains complex circuits, because it contains resistors that they are in series. As you see here, if you zoom in, we have R2, R6, and R5, which are in series, right? They are connected in series. Okay, we have R1 parallel to R4 and parallel to R3. So when we have a circuit that contains these two types, so that's what we refer to as complex circuit. So what's our job here is to is to simplify this complexity. Okay, so this is complex. We make it so simple. Look, compare between A and D. A, the circuit is too complex. In D, it's too simple. You see, we have only one resistance. So how to go through this? So first step, as you see here, R3 and R4 are in they are in series, right? Okay, so that's what we call or refer to as R34. Okay, so we add the value of R3 and R4. However, R3 and R4 are parallel to R1. So they are parallel, so we have to apply this equation. Okay, we have to apply 1 over R total equal 1 over R1, the first resistance, plus 1 over R34, the other side of the resistance. Okay, then, so we simplify the circuit, so then we have this shape. So we have R3 and R4, they are series, but they are parallel to R1. Okay, so that was the first step. As a second step, we simplify R1 and R3 and 4 in one resistor. So we call it R134. So you see here, we have R134. Okay, instead of two resistance, now we have one resistance. Now the shape of the circuit is too easy. Look at them, they are all in series, so we have to add them. It's straightforward. Okay, so we add the value of the resistors. Okay, R1, 2, 3, 4, 5, and 6. Okay, so that's how we simplify a complex circuit. Okay, so first we look where we can see series resistors are in series. Then we look at resistors they are connected in parallel, and then we add them easily. Bon, here are two simple questions as well. So let's read it together. 5.7. As more identical resistors are added to the circuit shown in the figure, the resistance between the points A and B will be. So if we have uh, if we have more resistance connected in parallel, what will happen between A and B? What do you think? The resistance will increase or decrease? Imagine adding here another resistance and another resistance. We put 10 resistance here. What will happen to the total resistance? The value will decrease. The value of the total resistance will decrease. Okay, it's not a common sense, but let's think about it. If we add more resistance, the resistance will increase. That's our common sense, right? Every time we are adding resistance, the resistance will increase between the points. But if they are connected in parallel, the value of the total resistance will decrease. Okay, if you go back to the equation, 1 over the resistance. Okay, so there is a inverse. Okay, so if we are adding more resistance, the value will decrease because there is inverse 1 over R. Okay, I will leave you think about question 5.8 and put me your answers in the comment. Please read it and choose either it's A, B, C, and D. Waiting your answers not on Classkick this time, but on the comment box below. So it's already 30 minutes. I'm about to finish chapter 5. We are about to finish chapter 5. Oh, I don't want to show you the answer. I forgot to eliminate. Okay, no worries. Okay, no, okay, I need to put the explanation, no problem. Okay, so here we go to section 7. Please, the one who volunteered, please also to include the page of this section in the comment as well, please. So here talking about the power, new concept, and energy. Okay, so power in electric circuit. So when talking about the power, okay, so we have three small equations that we have to take note of. So the power is equal to the current multiplied by the voltage. I think, or I am sure that you are already familiar with that equation. Okay, this is a simple, very simple equation of power where the current is equal, the power is equal to the current multiplied by the voltage. We can write it in another way, or equal to the I square multiplied by the resistance. Of course, if you replace the voltage by R multiplied by I, so that's what we get. Also, the power can be written as a third shape or third way of equation where delta V square over the resistance. So how to choose which equation to select in a question or in a problem? It also depends. It always depends on what? On the given. If in the given they gave me the resistance and the current, so of course I use this equation. If they gave me the voltage and the resistance, so I use this equation. So you can modify, you can play with the equation as you want, or depends on the given. Okay. Oh, I hope my phone. Okay, here is questions, slide number 6. I forgot the microphone. I hope the voice is clear. Test, test. Okay, anyway. So this is slide 6. Oh, يمكن هرجع أعيد الفيديو من الأول. الله. هلا بشوف بالآخر. Test, test. Okay, so this is slide 6 and this is the given. صار الظهر. Okay, so I equal 25 ampere, delta volt, voltage equal 10.5. This means I have to finish the video. Okay, and time is equal 10 minutes. Okay, you can convert it to seconds, of course. Okay, I'll leave you the freedom. I'll give you the freedom to solve this on slide 6 on a Classkick. Okay, here's another small example also. Question. Okay, so if the current through a resistance increased by a factor of 2, how does this affect the power that's dissipated? So you can use this equation, okay, to find out that if the resistance increased by a factor of 2, so it means doubled, how this will affect the power. So it will be so what if we increase, sorry, not the value of the resistance, the value of the current. So if the current through a resistance increased by 2, so we double the current. So because it's square, okay, to the power of 2, so the power will be multiplied by 4. It increased by a factor of 4. Okay. What about this question? All 3 light bulbs in the circuit shown in the figure are identical. They are the same. Which of the 3 shines the brightest? Okay. So what do you think? Okay. I will leave your answers for this question in the comment. Okay, and you can tell me why also. You can include your explanation as well. Okay, so this is 5.4. I hope I didn't put the answer. Okay, no worries. Okay, okay, the answer is C, but please put your explanation in the comment box. And that was for chapter 5. Thank you for listening. I hope it's not that long. See you in part 2 where we're solving these questions. Okay, see you next week. Thank you for watching and bye bye.